Look at a pitched roof or a steep stretch of highway. We intuitively know when an incline is severe. But to actually build that roof or pave that road, engineers need to translate that physical slope into precise numerical data. They do that using coordinates. This animated diagram illustrates how that translation works. Here we have two sets of stairs on a coordinate plane, one steep blue set and a shallower red set. If we overlay right-angled triangles on both, we can isolate two dimensions, the vertical height, which we call the rise, and the horizontal depth, which we call the run. The mathematical gradient is the ratio of that vertical rise to that horizontal run. To calculate this without drawing stairs every time, we use a single formula. By subtracting the y values to find the rise and dividing by the difference in the x values to find the run, we extract an exact number for any slope. Let's look at this coordinate plane showing points P at -4, 5 and Q at 4, 17. To find the gradient of the line connecting them, we substitute these specific coordinates directly into our fraction, 17 minus 5 on top, divided by 4 minus -4 on the bottom. Right here is where the most common calculation error occurs. Subtracting a negative number is the same operation as addition, so our denominator becomes 4 plus 4, giving us a final fraction of 12/8, which simplifies to a gradient of 1.5. That result of 1.5 tells us exactly how the line behaves. Because it is a positive number, the line slopes upward from left to right. If our calculation had resulted in a negative number, the line would travel in a downward descent. Knowing a line's gradient is useful, but defining the entire straight line requires an algebraic equation. The standard slope-intercept form is y equals mx plus c. However, equations are rarely presented to us in this neat format. Take a look at this equation on screen. 2y minus 6x equals 12. To find the true gradient, we have to isolate y. First, we move the 6x to the right side of the equal sign. Then, we divide the entire equation by 2. We are left with y equals 3x plus 6. The coefficient of x is our gradient, so in this case, the gradient is exactly 3. Sometimes we need to build an equation from scratch, using only a known gradient and a single point. For that, we use an alternative formula. Y minus y1 equals m times x minus x1. If we have a gradient of -2 passing through the point 3, -4, we drop those values into their corresponding slots, expand the brackets, and simplify to get our final equation. Y equals -2x plus 2. Deriving this equation is essentially decoding the DNA of the straight line. In this standard form, you have the rules needed to predict any precise coordinate along that path, infinitely in either direction. This animated diagram demonstrates how multiple straight lines interact. On the left, we see parallel lines. They have identical gradients, meaning they will never meet. On the right, we have perpendicular lines. These intersect at exactly 90 degrees, and their gradients are negative reciprocals of one another. Let's break down exactly what a negative reciprocal is. If our original line has a gradient of 2, finding the perpendicular gradient requires two specific actions. We flip the integer into a fraction, 1/2, and we invert the sign, giving us a perpendicular gradient of -1/2. Now, pause the video and try this yourself. Find the equation of a line parallel to x plus y minus 1 equals 0, passing through the point -1, 1. First, rewrite the equation to find your gradient of -1. Because the lines are parallel, keep the same gradient. Substitute the point into the formula, and you arrive at y equals -x. These precise relationships are the mathematical checks used to ensure railroad tracks remain parallel, or that vertical support beams meet horizontal floors at true right angles. Beyond direction and alignment, we often need to measure the physical length or magnitude of a line segment. This visual shows points P at 2, 1 and Q at 5, 5. By drawing a right-angled slope triangle between them, we can see the horizontal change is 3 and the vertical change is 4. Finding the magnitude of the line is an application of Pythagoras' theorem. The Pythagorean relationship translates into the formal magnitude equation, the square root of the change in x squared plus the change in y squared. Substitute our side lengths of 3 and 4 into the squares, giving us 9 plus 16. That equates to the square root of 25, which resolves to a magnitude of 5 units. This calculation bridges abstract geometry with tangible reality. This is exactly the mathematical logic that allows mapping software to compute the physical distance between two raw GPS coordinates. Before we finish, we need to differentiate the magnitude formula from the midpoint formula. Look at this side-by-side comparison. On the left, the distance formula relies on subtraction and squares to measure length. On the right, the midpoint formula relies on addition and division by 2 to locate a specific center coordinate. Let's apply that right-hand formula to find the exact middle of points A at 3, 4 and B at 5, 10. We add our x values of 3 and 5 and divide by 2 to get 4. We add our y values of 4 and 10 and divide by 2 to get 7. The resulting coordinate, 4, 7, is our precise midpoint. Calculating a midpoint is a standard task for engineers balancing weight distribution in a structural beam, or pilots determining the geographical center between two distant waypoints. We have covered the core foundations today: understanding slope direction, building linear equations, governing their interactions, and calculating both length and center. To make this manageable, here is your complete coordinate geometry toolkit. Quadrant 1 covers the gradient formula. Quadrant 2 outlines the slope-intercept equation forms. Quadrant 3 breaks down parallel and perpendicular rules, and Quadrant 4 contains the magnitude and midpoint formulas. Take a screenshot of this layout for your notes. These formulas provide the framework for defining paths, measuring distances, and centering structures in physical space. From civil engineering to digital mapping, coordinate geometry serves as a practical system for measuring and navigating the world.